Welcome back. So in this lecture, we talked about gas power spectral density. Power spectral density plays a crucial role in estimating the power of signals. Generally, average power can be found in time domain, the expression of which is quite familiar to everybody. If the mathematical representation of the signal is available, we can be able to estimate the average power. Okay, using the expression average power equals to limit t tends to infinity 1 over 2t minus t to t x square of t dt. Right? This is the expression for average power. However, it is not necessary that always the mathematical expression for signal is available. Take the case of noise. You cannot be able to represent the noise mathematically because noise is random and existing in multiple forms. So in such a scenario, when we cannot be able to estimate the average power in time domain, the ultimate option is to go for the frequency domain. The power, average power, when you talk about random process, we can call Pxx and Pxy or Pyx. This Pxx is corresponds to average power of a single random process, capital X of t, whereas xy or yx, these corresponds to two different random processes called as x of t and y of t. Pxy is the average power induced in random process y of t due to x of t, and Pyx is the average power induced in random process x of t due to y of t. So for estimation of this auto power or simply average power or crash power. Why crash power? This is crash power because we are estimating the power induced in one random process due to the another one. For estimation of these things, sometimes it is required for us to estimate the frequency spectrum. Okay, so in such a scenario, the average power, if I talk about cross power particularly in this lecture, the average cross power is the area under the cross power spectral density. Average cross power is the area under the cross power spectral density. Similarly, Pyx can also be given as 1 over 2 pi minus infinity to infinity s by x of omega d omega. Now, it can be auto power also. Simply what is the thing we can conclude is average power is the area under the power spectral density. It can be auto power spectral density or power spectral density or simply cross power spectral density. These Sxy of omega and Syx of omega can be represented mathematically as, okay, so S x y of omega equal to limit t tends to infinity expected value of x t star of omega into yt of omega by 2. Okay, what is xt of omega? Okay, xt of omega is the Fourier transformation of truncated sample function xt of t. Similarly, yt of omega is the Fourier transformation of yt of t, truncated portion of y of t. Of course, this asterisk or star indicates a conjugate. Similarly, what is Syx of omega also? Let me mention here. Okay, so S y x of omega can be represented as limit t tends to infinity 1 over 2t. I just better put it in another form. Okay. Yeah. Expected value of limit t tends to infinity. Expected value of y t star of omega into xt of omega by 2t. This is the expression for power spectral density SYX of omega, and we can estimate the crash power using either of these. Okay, so the main objective of this lecture is to discuss about the properties of crash power spectral density. So the first and foremost important property is crash power spectral density and time average of cross correlation function form a Fourier transform phi. This is the mathematical expression for the first property. Sxy of omega is the cross power spectral density. This A of stands for time average. We know E of means statistical average. A of means time average. Okay. So let us go ahead with the proof for this statement. Whatever statement we have mentioned here, let us go with the proof, which states, okay, let us begin with definition. Okay, so proof. This is the most important property which is used for other properties also. It is known that SYX of omega equals to limit t tends to infinity expected value of xt star of omega, that is conjugate, and yt of omega by 2t. Let me define, let me take a case. What is xt of omega? Xt of omega is the Fourier transform now. So it can be given as Fourier transformation of xt of t. Okay, which can be generally, I can just mention what is definition of Fourier transform. Minus infinity to infinity xt of t e power minus j omega t dt. However, this truncated portion is existing between minus t to t only. So within that context, we can represent this as x of t e power minus j omega t dt. Okay. This can be the expression for xt of omega. Similarly, now I go for yt of omega simultaneously. Yt of omega. This is equals to Fourier transformation of yt of t. Okay, so this can be written as minus infinity to infinity yt of t e power minus j omega t dt. However, this is truncated portion. If it is existing between minus t to t only, so within that interval, it is equals to minus t to t. So instead of taking e power minus j omega t, I just take it as t1 into e power minus j omega t1 dt. Why this difference in t and t1 is to differentiate between the two different time instants. Because x of t corresponds to one random variable or one random process at one time instant. Y of t corresponds to another random process and then random variable at another time instance. So to differentiate between those, okay, we will take a t and t1, right? Now let us substitute the same in the definition of power spectral density. That is S x y of omega equals to limit t tends to infinity, okay, 1 over 2t, okay, expected value of first one minus t to t, okay, we have taken x of t e power minus j omega t dt. Actually, this becomes plus because it's conjugate. Similarly, minus t to t y of t1, another one, e power minus j omega t1 dt1. Hope it is clear. This is not a conjugate. So minus is as it is. This is a conjugate. So minus becomes plus. If you further simplify this, limit t tends to infinity, 1 over 2t minus t to t. Again, we substitute minus t to t. Expected value of x of t into y of t1 e power minus j omega t1 minus t dt1 dt. Okay, so if this expression is simplified further, okay, so this can be written as limit t tends to infinity, 1 over 2t minus t qt. This term is the cross correlation function, which we can write as rxy of t comma t1, because this is one random process. This is another random process. This is one random variable at time instant t. This is another random variable at another time instant t1. So now modify this minus t to t e power minus j omega t1 minus t dt1 dt. Okay. Now what we do? We apply inverse Fourier transform on both sides. Okay. So what is the meaning of inverse Fourier transform? Well, apply. Okay. So this can be mentioned as 1 over 2 pi minus infinity to infinity s xy of omega e power j omega tau d omega, which is equal to, here again, let us simplify directly, limit t tends to infinity, 1 over 2t minus t to t. This is rxy of t comma t1. Okay, right? Into e power minus j omega t1 minus t into e power j omega tau into d omega d t1 d, right? Okay. So this will be leading towards, this is equal to limit t tends to infinity, 1 by 2t minus t to t r x y of t comma t1 into minus, here one more integration of course will come there. Okay, there are two integrations have been mentioned. One is minus infinity to infinity, second one is minus t to t. So minus t to t here, 1 over 2 pi minus infinity to infinity e power minus j omega into tau plus t1 minus t d omega dt1 dt, right? Okay. This is equals to, so by observing this expression, you can see this is the definition of inverse Fourier transform, which will be an impulse function. Limit t tends to infinity, 1 over 2t minus t to t r x y of t comma t1. Okay, then minus t to t. This is inverse Fourier transform of this is del of tau plus tau1 minus t dt1 d, or can also be taken as del of t minus t1 minus tau also. It is not an issue. So if it is clearly observed, area under the impulse function is always unity. Okay. Area under the impulse function is unity. So this will be equal to irrespective of the polarities, this will be equal to limit t tends to infinity 1 over 2t minus t to t r x y of t comma t1 dt. If I replace t1 equals to t plus tau, because this is another time instance, no, what happens? This is equal to limit t tends to infinity 1 over 2t minus t to t r x y of t comma t plus tau dt. From the definition of time averages, we know this is nothing but a of r x y of t comma t plus tau t plus tau. However, if we assume that the random process x of t and y of t are jointly wide sense stationary, if x of t and y of t are jointly wide sense stationary, then what happens? Rxy of t comma t plus tau equals to Rxy of tau, independent of time, right? Now, as they are independent of time, automatically one over 2 pi minus infinity to infinity s xy of omega e power j omega tau d omega equal to a of r, not a of, we should not do it because we are assuming the stationarity. Rxx of tau, which means what it means. Rxx of tau can be obtained from the knowledge of cross power spectral density. That is why we say cross power spectral density and auto cross correlation function form a Fourier transform pair, provided they are stationary. We need to remember that the random process x of t and y of t must be wide and stationary. Then only this condition is satisfied. Okay. Then let us go ahead with the remaining properties. Property number 2. Real part of s x y of omega and s yx of omega are even functions. Even functions of omega. Okay, real part of these are even functions of omega. So how it can be proved, we'll see. We assume, let all the properties left over are only for stationary process. Let x of t and y of t are jointly wide sense stationary. Okay. So what happens? If they are jointly stationary, it means they are going to be forming a Fourier transform pair, right? This is equals to pair Rxy of tau as well as S xy of omega are a pair. So we substitute this. Sxy of omega equal to Fourier transform of R xy of tau, cross correlation, assuming they are stationary. So if we substitute minus infinity to infinity R xy of tau into e power minus j omega tau d tau. E power minus j theta is always known as cos theta minus j sin theta. So if we substitute that, this is equals to minus infinity to infinity r x y of tau into cos omega tau minus j sin omega tau theta. Okay. So what is the real part of this cos sin? So among these two, real part is real part of s xy of omega, real part of sxy of omega will be equals to minus infinity to infinity r x y of tau cos omega tau d tau. This is first one. For proving the it is an even function, we have to also estimate what is the real part of s xy of minus omega. So which is given as it is minus omega, right? So I can represent this same as minus infinity to infinity Fourier transform no sxy of rxy of tau into in the place of minus j omega tau, we will be getting plus j omega tau, right? Okay, actually it is e power minus j omega tau, but here we have mentioned minus omega, so we have to put minus here, minus of minus plus. So correspondingly, again replace. This is equal to minus infinity to infinity r x y of tau into cos omega tau plus j sin omega tau d tau. This is equal to e minus infinity to infinity r x y of tau cos omega tau plus j r x y of tau sin omega tau d tau. Now the real part of this is okay. Real part of s xy of omega minus is equals to again minus infinity to infinity r xy of tau cos omega tau. So what we can conclude as real of sxy of omega is equal to real of s x y of minus omega, okay, minus omega. Real part of ssy of omega is a even function of omega, right? Real part of sxy of omega is real is even function, not real. Yeah, is an even function of omega. Okay. Similarly, we can prove for Sx S by x of omega also. Okay. Now let me go for the third property. Next one. Which is the third one? Imaginary part of S xy of omega or imaginary part of S yx of omega are odd functions of omega. Earlier case is even function. Real part is even function, whereas imaginary part is odd function. What is the meaning of odd function? We know if x of t equals to minus of x of minus t, we call such a function as an odd function. So Let us proceed in the same manner as we have done earlier. So first let us put what exactly the definition of SYX of SXY of omega. SXY of omega equals to Fourier transform of S, okay, RXY of tau R X Y of tau, which is equals to minus infinity to infinity R X Y of tau into e power minus j omega tau d tau. I replace this with constant sign. So minus infinity to infinity R X Y of tau into cos omega tau minus j sin omega tau d tau. Right? Okay. Now what is required for us? Imaginary part. Okay. What is the imaginary part of this sine term? No, we'll see. So imaginary part of Sxy of omega can be given as, I say, minus also, minus of minus infinity to infinity Rxy of tau sine omega tau d tau. Let us go for we have to prove that it is odd function. No, so let me just go for negative one also. What is Sxy of minus omega? So automatically this will take me to Rxy of tau e power j omega tau d tau d tau. Why here minus is missing? Minus of minus plus. So this is equals to minus infinity to infinity Rxy of tau into cos omega tau plus j sin omega tau d tau. Okay, what is their imaginary part now? Imaginary part of Sxy of minus omega equal to, okay, equal to simply minus infinity to infinity Rxy of tau sin omega tau d tau. Okay, this will be further equal to it is simply can be written as nothing but minus of imaginary part of Sxy of omega. Thus, Sxy of omega imaginary part is an odd function of omega. Odd function of omega. That is about the third property. These properties will be generally useful for solving the problems actually. The advantage of all any property, not only the case of cross power spectral density, only any property, their significance is they will help in solving the problems. Let us go with the next property. Let there be two random processes, capital X of t and capital Y of t, two random processes, which are orthogonal. Okay, I think this is the fourth property. Then random processor X of t and Y of t are orthogonal. Okay, orthogonal. Then power spectral density cross is equal to 0. Cross power spectral density will be 0. This is a very simple property. You can easily prove this. Because they are orthogonal, we cannot have power induced in one due to another. So Sxy of omega equal to Fourier transformation of Rxy of tau, right? This is equal to minus infinity to infinity Rxy of tau e power minus j omega tau d tau. However, when two random processes are orthogonal, cross correlation function is equal to 0. Okay, when two random processes x of t and y of t are orthogonal, cross correlation is 0. So automatically sxy of omega equal to 0. For any two orthogonal random processes, x of t and y of t, cross power spectral density will be 0. Okay. Then fifth one. Let there be, let capital X of t and capital Y of t be two statistically independent, TW2, statistically independent random processes. Statistically independent random process. Say, of course, they are stationary. That is second issue. Then S x y of omega equals to 2 into pi into x bar y bar into del of omega. They must be statistically independent. So how we can proceed with the proof? Let us see now. Again, we go by in majority of the properties which differential. It is known that Sxy of omega equals to Fourier transformation of Rxy of tau equals to minus infinity to infinity Rxy of tau into e power minus j omega tau theta. This is equals to, we know what is the definition of cross correlation. Expected value of E of x of t, okay, into y of t plus 2. Definition of cross correlation. E power minus j omega tau d tau. But they are statistically independent. No? When two random variables are statistically independent, E of xy equals to E of x into E of y. So this will turn into E of x of t into E of y of t plus tau into e power minus j omega tau d2. However, y of t is x of t are stationary. When a random process is stationary, mean value constant. So automatically this will become e of y of t. Both e of x of t and e of y of t are constants, right? They are mean values, right? So what happens? This will be equals to x bar e of x of t, y bar e of y of t into minus infinity to infinity e power minus j omega tau d tau. This is almost equals to Fourier transformation of 1. So the Fourier transformation of 1 is 2 pi into del of omega. So finally, it will leads to 2 pi x bar y bar into del of omega. Okay. When two random processes are statistically independent, their cross power spectral density will be equal to this. Then, last property, let us prove and check whether conjugate property. Okay. So, S x y of omega sixth one is equals to S yx of minus omega. Okay. So let us first of all prove. We know what is the definition of these two things. We know like this. What is Sxy of omega? First of all, let us write the definitions. Minus infinity to infinity Fourier transformation of Rxy of tau. No. So minus j omega tau d tau. Similarly, what is Syx of omega? So minus infinity to infinity Ryx of tau e power minus j omega tau d tau. This is Sxy of omega. So Rxy, this is Syx of omega. So Ryx. Remaining there's no change. So what is required for me now? I go in this manner. I just concentrate on the second term and proceed with the property proof. S yx of minus omega means replace there minus infinity to infinity r x y r yx of tau. I just need to modify this. 1 second. Yeah. R y x of tau e power minus j omega minus omega tau d tau. Why? Because I have taken minus omega, I have considered minus omega. Then I do small adjustment here. I replace this minus infinity to infinity r y x of tau into e power minus j omega minus tau d tau. I'll replace this. Now let minus tau equal to u. So d tau equal to minus du. Okay. Tau equals to minus u. So let us replace this. This is equal to minus infinity to infinity. Here tau is present. So this will become r yx of minus u e power minus j omega u minus du. This will be actually plus infinity to minus infinity. But because of this minus same, I can rearrange the signatures. Minus infinity to infinity, r yx of minus u e power minus j omega u. Hope it is clear. Initially, limits are minus infinity to plus infinity, but we have replaced with u. So limits are plus infinity to minus infinity. But because of this minus signature, they are again rearranged. Then the properties of cross correlation, we know Rxy of tau equals to Ryx of minus tau. So what is happening here? S y x of minus omega equals to minus infinity to infinity r x y of tau into e power minus j omega tau into d tau. What happened to u? U is a dummy variable. So I can replace with tau also. Right? Hope understood. Otherwise, I can write here everywhere it u know minus infinity to infinity r x y of minus u e power minus j omega u du. This u I have replaced and we have simplified. Because of this property. Right? That's conclusion. What is the conclusion? S x y of omega equal to S yx of minus omega. From the fundamentals of Fourier transform, I can also mention this as S yx conjugate also. Okay, so this is about the properties of cross power spectral density. Hope the proofs were well understood. See you in the next lecture. Keep on learning. These properties need practice, because in the examination point of view, we should be able to practice this much. Thank you all.